Welcome. Today we want to explain in details how an inverter works. You see, electricity is everywhere around us, but not all electricity is the same. The power in your battery is direct current DC, the power in your wall socket is alternating current AC. An inverter is the device that bridges this gap. It converts DC into AC so we can use our everyday appliances. Here is a 12-volt battery on one side and AC bulb on the other side with an inverter in between. It's a middleman. We are going to explain how an inverter works from the basics. If you are new to this channel, please subscribe, like, and share this video. To create AC, we need to take steady DC and make it alternate. That starts with an oscillator, a circuit that generates pulses or waveforms. Think of it as a rhythm machine that decides when to turn switches on and off. Oscillators can be built using simple ICs like the 555 timer, dedicated PWM chips like the SG3524 or TL494, or even microcontrollers. They create square, quasi-sine, or pure sine pulses, which form the timing backbone of the inverter. Oscillation is an essential stage in process of DC to AC inversion. Conversion from AC to DC requires simple setup, but in this context, it's a different ballgame.
Now let's pause for a moment and look deeper. The oscillator might seem like a tiny section of the inverter circuit, but it's actually the timing brain behind everything. It controls how fast the switching devices turn on and off, setting the rhythm that defines the entire operation. When the oscillator runs steady and accurate, the inverter delivers a smooth, clean AC output. But if the frequency drifts or becomes unstable, the output turns rough and noisy, affecting both performance and efficiency. So, in simple terms, the oscillator doesn't just start the process, it keeps the inverter alive, coordinated, and consistent. Now let's talk about the driver stage.
The oscillator itself cannot drive big transistors directly. The pulses are too weak. That's why we need a driver stage. The driver acts like a muscle amplifier. It takes the small oscillator signal and turns it into strong, sharp pulses that can fully control MOSFETs or IGBTs. Good drivers switch fast. That reduces wasted heat and makes the inverter efficient. They also add a safety margin called dead time so that two switches are never on at the same time, which would cause a short circuit. At this stage, the pulse from the oscillator is made sharp and strong.
The driver stage in an inverter acts as a bridge between the control IC and the power switches, MOSFETs or IGBTs. It amplifies weak PWM signals, providing enough voltage and current to switch the transistors rapidly and efficiently. It also performs voltage level shifting, ensuring proper gate drive, and provides isolation to protect the control circuit from high voltages. The driver includes dead time control to prevent shoot-through, and often has safety features like undervoltage and overcurrent protection. In simple terms, it's the powerful messenger that delivers strong, clean, and precise signals to the power stage, ensuring smooth, safe, and efficient inverter operation.
With the driver in place, the heavy lifting begins. Power transistors like MOSFETs or IGBTs take energy directly from the battery and switch it on and off in sync with the oscillator. There are different configurations. In a simple push-pull design, two switches alternately drive a transformer winding. In a half-bridge or full bridge, four switches form an H-bridge that flips the current back and forth. The output at this stage is a high-power AC-like waveform, but it's still a square wave. The push-pull configuration clearly differs from the H-bridge configuration as shown here. Now that we have a powerful switched waveform, it's time to shape the voltage to match our needs. This is where the transformer stage comes in. In low-frequency inverters, those pulsing DC signals are sent straight into a large transformer. The transformer has two main jobs. First, it isolates the battery side from the AC output for safety. Second, it steps the voltage up or down, depending on the application. For example, a 12-volt battery might feed the primary winding, and the transformer boosts this up to 220 volts AC on the secondary side, or 120 volts AC on the secondary side. The exact voltage change is set by the ratio of turns in the transformer's windings. But what about high-frequency inverters? Here the switching happens at tens of thousands of cycles per second. This allows the use of a much smaller, lighter high-frequency transformer, often built with ferrite cores. The principle is the same. Voltage is stepped up or down and isolated, but everything is more compact. After this, the high-frequency AC is rectified and filtered to recreate a smooth AC output. Let's see these differences up close. Here's a traditional low-frequency transformer. Notice how bulky and heavy it is. Now, compare it to this compact high-frequency transformer from a modern inverter. The difference in size and weight is dramatic thanks to the higher switching speed. Take a closer look at the windings, the core materials, and the physical design. Each type plays a crucial role in how efficiently and safely the inverter delivers usable AC power. Most appliances don't run smoothly on square waves, that's why we need wave shaping. Modified square wave inverters insert pauses to better imitate AC. Pure sine wave inverters go further, using techniques like SPWM, sinusoidal pulse width modulation. In SPWM, the width of each switching pulse is varied to approximate a sine wave. Then, filters made of inductors and capacitors smooth the waveform into a clean sinusoid. Real inverters don't just generate AC, they also regulate it. A feedback circuit monitors the output voltage and frequency, and adjusts the oscillator duty cycle to keep the output stable, even as loads change. Feedback also enables protections. If the battery is too low, if the load is too heavy, or if the system overheats, the inverter can shut down safely. Sensing AC output, comparing it with a reference, then adjusting the PWM. Protection is a critical part of any inverter. Without it, even the best design can fail quickly. Some of the key protection circuits include low voltage cutoff. When the battery voltage drops too low, the inverter shuts down to prevent over-discharging and permanent battery damage. Overload protection. If you plug in more appliances than the inverter is rated for, the circuit senses the excess current and shuts down or reduces output to protect the MOSFETs and transformer. Short circuit protection. In case of a direct short at the output, the inverter instantly cuts off power to prevent catastrophic damage. Thermal protection. Temperature sensors on the heatsink monitor how